The reciprocity theorem is based on the observation that in an electrical network, there is a two-way relationship between the voltages and currents in the circuit. If we exchange the positions of the voltage and current sources in the circuit at different branches, there won't be any change in the distribution of current in that branch. This mutual or reciprocal effect where the voltage and current can be interchanged without altering the behavior of the circuit is the core of the reciprocity theorem. In this session, we'll explore that in detail. Let us consider an electrical circuit consisting of a voltage source E and a network of resistors. The current flowing through some part in the circuit is I, and to detect the presence of the current, an ammeter has been placed. Then the reciprocity theorem states that in any linear bilateral network, if a source of EMF E in any branch produces a current I in any other branch, then the same EMF acting in the second branch would produce the same current I in the first branch. That is, if we swap the voltage and the current sources, then the distribution of the current in the circuit remains unchanged. That is, the same current I flows through the branch where the voltage source were actually placed. In this circuit, the voltage source is the cause and the current produced in this branch is the effect. Then according to the reciprocity theorem, if we exchange the position of the cause and effect in the circuit, then also the circuit remains consistent. That is the reason why this is called the reciprocity theorem. In simple terms, it essentially means is that E and I in a circuit are mutually transferable. And the ratio E over I is known as the transfer resistance or impedance of the AC systems. Reciprocity theorem also indicates that an ideal voltage source and an ideal ammeter in any network can be interchanged without any change in the ammeter reading. And the same is the case with the interchange of an ideal current source and an ideal voltmeter. Let's do this problem for a better understanding of the theorem. In the network of figure A, find ammeter current when battery is at A and ammeter is at B. That is, battery is located at position A and what you see here is an ammeter which is located at point B. The second part is to calculate the ammeter current when the battery is at B and the ammeter is at point A. And then finally we have to calculate the transfer resistance. We shall solve one by one. Solution for part A. We have to find out the current that is going to flow through the 1 ohm resistor because of the 36 volt supply placed at A. For that, we have to first find the battery current, that is the current that is generated by the battery. Let's denote that by I dash. If we want to calculate that, we'll have to find out the total resistance in the circuit. In this circuit, we have a 2 ohm, 3 ohm, 4 ohm, 12 ohm and then 1 ohm resistors, and then we can replace the ammeter by its internal resistance. If the internal resistance is very small, then this can be approximately taken to be 0, or we can simply short the circuit. In the problem, the internal resistance is not given, so that we can simply short the circuit and the circuit will now be like this. Four ohm, 12 ohm, 1 ohm, 3 ohm and 2 ohm. This is point C, A, and this is point B. We'll first calculate the equivalent resistance between points C and B. So between C and B, the 12 ohm resistor is in parallel with a series combination of 3 and 1. Therefore, we can write this as 12 multiplied by 4 divided by 12 plus 4, and this is equal to 3 ohms. Now this 3 ohm resistor is in a series combination with the 2 ohm and 4 ohm resistors. Therefore, the total resistance in the circuit is 2 plus 3 plus 4, that is equal to 9 ohm. Therefore, the battery current, that is I dash, this is equal to the total voltage, that is 36 divided by the total resistance, that is 9, which is equal to 4 amperes. So we have calculated the total current in the circuit, and then the ammeter current can be calculated by using the current divider rule. According to the current divider rule, the current that is going to flow through the ammeter or the 1 ohm resistor is given by the total current multiplied by resistance in the other branch, that is 12, divided by the total resistance in the loop, that is 12 plus 3 plus 1, and we can find that this is equal to 3 ampere. That is, a 36 volt supply which is placed at A will result in the flow of a 3 ampere current across the ammeter. Now let us consider part B of the problem. That is, we have swapped the position of the ammeter and the voltmeter. We first have to calculate the total current in the circuit, that is I dash. For that, we can replace the ammeter by a short circuit because the internal resistance is almost equal to 0. Therefore, the circuit becomes we now have to calculate the equivalent resistance between points C and D. Between C and D, we have the 4 ohm and 2 ohm resistors are in series, and they are in a parallel combination with the 12 ohm resistor. That is, 12 ohm resistor is in a parallel combination with a series combination of 2 and 4. This is 12 in parallel with 6. Therefore, this is 12 multiplied by 6 divided by 12 plus 6, and this is equal to 4 ohm. Now the total resistance in the circuit is given by 1 plus 3 plus the equivalent resistance between C and D, which is 4, and this is equal to 8 ohms. The battery current is 36 volt divided by 8 ohm, and that is equal to 4.5 ampere. And we can calculate the ammeter current. So this is I dash, battery current is I dash, and the current through the ammeter, this is I, which is given by the total current multiplied by resistance in the other branch, that is 12, divided by total resistance in the loop, that is 12 plus 2 plus 4, and this will be equal to 3 ampere. So this proves the validity of the reciprocity theorem. In part A of the problem, we had the voltage source at point A and the ammeter at point B. Now in the second part of the problem, we interchanged the position of the voltage source and the current source. So we took the voltage source to point B and the ammeter to point A. In both cases, we found that the current that is recorded by the ammeter is 3 amperes. This indicates that in any linear bilateral network, the location of an ideal voltage source and an ideal ammeter can be interchanged without any change in the ammeter reading. We shall now do the final part of the problem, that is to calculate the transfer resistance. The transfer resistance is nothing but E over I, and this is equal to 36 divided by 3, which is equal to 12 ohms. Let's do one more problem. This problem has two parts and we will see that one by one. In part A of the problem, we have to calculate the currents in the various branches of the network, which is shown in the figure. So this is a bridge network consisting of a network of resistors and a 1 volt voltage source. The direction of the various currents in the circuit are given, and we have to calculate the currents in the various branches of the network. Let's begin solving the problem by marking the different currents in the circuit. So starting from A, at node A we have 3 currents, and let us mark this current as I1 and this current as I2. When I1 reaches node B, it splits into two. One part goes through the 8 ohm resistor and the other part goes through the 4 ohm resistor. Let us denote the current that is flowing through the 8 ohm resistor as I3. Now the current that is going to flow through the 4 ohm resistor is I1 minus I3. At node D, currents I2 and I3 combine, and the current that will flow across the 5 ohm resistor is I2 plus I3. At node C, I1 minus I3 and I2 plus I3 combine, and the current that is going to flow through the 10 ohm resistor is I1 plus I2. In the next step, we have to find the various currents in the circuit, that is the value of I1, I2 and I3. To solve the various currents in the circuit, we can use the Kirchhoff's second law. We have 3 unknowns, I1, I2 and I3, and then we have to frame 3 equations to solve the 3 unknowns. For that, let us consider loop ABDA first. We will mark the polarity of various resistors in the circuit first. The direction of the current in the 2 ohm resistor indicates that this side is positive and this side is negative. In the case of the 8 ohm resistor, this side will be positive and this side will be negative. And in the case of the 6 ohm resistor, this side is positive and this side is negative. We have marked the polarity of the potential drops in the circuit. Now we are analyzing the circuit in the clockwise direction. As we move from A to B, we see a potential drop. Therefore, the potential drop is negative of 2 times the current I1. And as we move from branch B to D, we again see a potential drop, and therefore this is negative of 8 times I3. And as we move from D to A, we see a potential rise, and therefore this is 6 multiplied by I2, and this is equal to 0. From where we will get the first equation, I1 minus 3I2 plus 4I3 equal to 0. This is the first equation. For the second equation, we will consider the loop BCDB, and we will analyze the circuit in the clockwise direction. The various polarities in the circuit has to be marked first. In the case of the 4 ohm resistor, the side near to the node B will be positive and the node C will be negative. In the case of the 5 ohm resistor, this side will be negative and this side will be positive. And in the case of 8 ohm resistor, this side will be positive and this side will be negative. We have found out the current through the 4 ohm resistor as I1 minus I3, and that through the 5 ohm resistor as I2 plus I3, and the current flowing through the 8 ohm resistor is I3. We'll start from node B. As we move across BC, we see a fall in potential. Therefore, this is 4 times I1 minus I3. And as we move from C to D, we see a rise in potential. So that is 5 times I2 plus I3. And as we move from D to B, we again see a rise in potential, and that is given by 8 times I3. And that is equal to 0. From where we'll get the second equation, 4I1 minus 5I3 minus 17I3 equal to 0. To frame the third equation, we'll consider the loop A, B, C, E, A. Across the 2 ohm resistor, this side will be positive and this side will be negative. 4 ohm resistor, this is positive and this is negative. And for the 10 ohm resistor, this side is positive and this side is negative. And in the case of voltage source, this side is positive and this side is negative. We are going to analyze the circuit in the clockwise direction. The current through the 2 ohm resistor is I1. That through the 4 ohm resistor is I1 minus I3. And the current through the 10 ohm resistor is I1 plus I2. And as we move from A to B, we see a fall in potential. Therefore, the fall in potential is 2 times I1. And as we move from B to C, we again see a fall in potential, that is given by 4 multiplied by I1 minus I3. And as we move from C to E, we again see a fall in potential, therefore that is negative of 10 times I1 plus I2. Then for the voltage source, this is plus 1. So this is equal to 0. From where we will get the third equation, 16I1 plus 10I2 minus 4I3 equal to 1. So this is the third equation. We can now solve for I1, I2 and I3. And when we solve I1, I2, I3, we will get I1 as equal to 0.494 ampere. I2 as equal to 0.0229 ampere. And then I3 as equal to 0.0049 ampere. The current through the 1 volt power supply is given by I1 plus I2. Therefore, this is given by I1 plus I2 equal to 0.0723 ampere. Now the second part of the problem. Utilize the principle of superposition and reciprocity theorem together to find the value of the current in the 1 volt battery circuit when an EMF of 2 volts is added in branch BD, opposing the flow of original current in that branch. That is, in branch BD, the current that is flowing is I3, and in addition to that, we have added a 2 volt supply. And we have to calculate the value of the current in the 1 volt battery circuit when we add the 2 volt supply in branch BD. And that has to be done using the superposition and reciprocity theorem. Let's see how. In part A, we only had the 1 volt supply in the circuit, and the various currents in the circuit are I1, I2 and then I3. We found those values as I1 equal to 0.494 amperes, I2 as equal to 0.0229 amperes, and then I3 as equal to 0.0049 ampere. Now the current in the branch CEA is I1 plus I2, that is I1 plus I2, and we found that as equal to 0.0723 amperes. Now let us assume that we have taken the 1 volt supply from branch CEA and then placed it in BD as shown in this figure. We saw that the 1 volt battery in branch CEA produced a current I3 equal to 0.0049 ampere in branch BD. Then, according to the reciprocity theorem, if 1 volt battery were transferred to branch BD, then it would produce a current of 0.0049 ampere in branch CEA. And if you are connecting a 2 volt supply, then the current that is going to flow across CEA will be 2 times 0.0049 ampere. That is, a battery of 2 volt will produce a current of negative 2 times 0.0049, because the current from the 2 volt supply is going to oppose the current I3. Therefore, the current will be having a negative sign, and this will be equal to negative of 0.0098 ampere. Hence, the new current in branch CEA will be, initially there were I1 plus I2, and then because of the 2 volt supply, the current that is going to flow in this branch will be 0.0098. The new current will be 0.0723 minus 0.0098, and that is equal to 0.0625 ampere. This problem thus demonstrates the use of reciprocity theorem in solving complex electrical circuits.